All right, everyone. Once again, we have our special guest star, Kuldeep Meel, to talk about constraint satisfaction problems.
All right. Okay, so I hope you had a fun spring break. Do you remember what we were doing before spring break? Well, we were looking at this idea called constraint satisfaction problems. So what are constraint satisfaction problems? A set of variables. These variables can take value from a domain, and we have a set of constraints on these variables. Okay. And what we want to do is to find an assignment to these variables so that all the constraints are satisfied. And we looked at few of, why we are interested in this paradigm of constraint satisfaction problems. Well, there are lots of problems that can be just naturally formulated as a CSP problem. You want to figure out what, in what classrooms and when to assign a particular course. It's just a natural CSP problem. And we have been looking at this problem of n queens, which I'm again going to come back today. Why we care about this? Because one real power of the CSP is that you formulate into one unified interface, and then you can just focus on developing a general purpose algorithm, and you suddenly get a powerful tool that you can apply in a lot of settings. Your homework assignment this week, you are hopefully exploring uses of this tool, AI CPOR tools. And we started looking at this algorithm called backtracking. We got some ideas about inference. We are going to go into more detail and a little bit about some heuristics that make these tools really work. Last time I alluded to something, so I thought it will be worthwhile to revisit one aspect. Look, if you have something that is really powerful by which you can model a lot of situations, it would mean that you had to give up somewhere. And where we end up giving up is the problems that can be modeled by CSPs. Even though they might look very simple, they can be very hard algorithmically. What do I mean by that? If I give an assignment, then checking whether the assignment satisfies all the constraints is very simple, right? You substitute the value in every constraint, and then you check whether it satisfies or not. But finding an assignment that satisfies all the constraints may be very hard. In particular, these problems are what are called NP. So NP are the class of problems for where checking is easy, but finding one, we don't know of any efficient algorithm, polynomial time algorithm so far. The best known algorithms are exponential. And these problems remain NP even if you look at some restrictions. For example, you can say, look, I want you to come up with a CSP problem where every constraint has only 2 variables. Okay, so that kind of looks like a simple problem. You have a set of variables and you have constraints. Every constraint always talks about only at most 2 variables. Even in that case, the problem turns out to be NP hard. In fact, you could say that, look, I want to look at problems where every variable can only take 2 values. And that again turns out to be a hard problem. In particular, this is called the problem of satisfiability set. There are, of course, some cases that are polynomial. So one such case is where you say that, look, every variable, every constraint can only be over 2 variables at most. And every variable can only take Boolean 2 values. So you can think like that's a very, very restricted case where it turns out to be polynomial time. So kind of most general settings of this constraint would mean that these problems are going to be hard in the worst case. And what that translates to is that we are going to come up with algorithms that are exponential in the worst case. But that's okay. We don't also live just for the worst case in life. So what we want is algorithms that work well in practice, okay, even if they might be exponential in the worst case. So this is where we left off last time. We were discussing this algorithm called improved backtracking. So what is the backtracking search? You go and pick a variable, you assign the variable a value, What value should we assign? We should make sure that we don't assign a value that already violates the constraints. So let's go back to some of these. I want to show you some animation that we were looking at last time. Okay, so here is what the algorithm would do. So every time it has to, remember, every time it has to place a queen in one of the columns, and the next time it's trying to place the queen, it will make sure that it places the queen so that it doesn't already get attacked by everything that was all there. But it may happen that it has placed a queen, and then once it places, it tries to place the other queens, there is no possibility, then you end up backtracking. Okay? Let's just give you an idea about what we are doing. So the set of variables here are the queens that we are going to place in each of the columns. So what we do, first we go and place the queen in the first column, then we go and figure out where to place the queen in the second column, then third column, fourth column, and so forth. But it may happen that at some point there is no way to place the queen, so we end up backtracking. And that's what this algorithm is showing. Let's go back to the case of 4 queens. So in case of 4 queens, if you remember, what we had is that you try to figure out where to place the first queen, then you try to place the second queen. So maybe we can also try to draw this. So we go and try to place the first queen. Let's say right now we are going to go over, why should we put the first queen in the first column? Right now we are just going to go with one fixed ordering. I'm going to revisit this question as well. In what row to place the first queen? Let's say for now we are going to try to place it in the first row, then second, third, and fourth. So once we have placed the first queen in the first row, we want to figure out where should we place the second queen. It does not make sense to place the second queen in the first row or the second row because it is going to get attacked, right? So we place the second queen in the third row. And then we try to figure out where can we place the third queen. Well, it turns out that there is no kind of any spot for the third queen to place, right? Because if we place it here, it gets attacked by the queen 1. We place it here, gets attacked by queen 2, here and here, so on. Maybe we could try to place the queen on the fourth row. In that case, for the second queen, there is a possibility. For the third queen. But for the fourth queen, again, we don't find any other possibility. So we have to backtrack. And here, backtracking would mean that we would try to put the first queen in the second row. Okay? Where we left off last week, 2 weeks ago, was can we minimize the number of backtracks that we are doing? Is it possible that after we place the first queen, we can figure out that, look, there is no possibility of placing rest of the queens, so we should immediately backtrack. Okay? Let's try to go back to what we were discussing last time. So we place the first queen over here. And without placing any of the other queens, I would like to be able to infer that there is no possibility of placing rest of the queens, so that no 2 queens attack each other. If I could infer that, then I could immediately backtrack. So what we want to do is to be able to backtrack immediately rather than trying out to place the second queen and the third queen and so on. Okay? All right, so let's try to see how we can infer such an something like this. So what we have done so far is to figure out where to place the first queen. Okay. So we have, I'm going to use, remember we were using variables x1 to x4. So x1 equals to 1 indicates that the first queen is placed in the row 1. So at this point, a few things that are maybe worthwhile to think about. So every variable has a domain from which it takes values. Once you say that the first queen is assigned to value 1, then what is its domain? Well, earlier the domain of possible values it could take were 4, right? 1, 2, 3, 4. What happens to the domain after you get assigned a value? Sorry? We removed one or we removed everything else? Domain is a set of possible values you can take. So now when we say that x1 must take value 1, we say it cannot take other possible values. So we are going to use some notion of current domain. Okay, so the current domain of this variable is now just 1, right? Because it cannot take any other values. So let's use some notation as well. So d hat of x1 is 1. So what happened right now? We took some action and that the domain of the variable until we made this assignment was 1, 2, 3, 4. And after we make this assignment, the current domain of the variable has changed to just 1. Okay? Domain is set of values. So now that the current domain of the variable has changed, what is it that we can infer up? What should we do now? Find the domains of the other variables. Maybe that might change, right? Which other variables? There are 3 other possible queens. 2, 3, 4. Which one should we look at? The second one? What about third one, fourth one? All right, so let's see. Maybe we can, let's start with the second one for now. So what is the constraint we have? We have a constraint that it says that, look, you should not attack x1 and x3. Sorry, x1 and x2. Okay? We also have a constraint that said don't attack x2 and x3. Which of the constraints we should be looking at right now? We have 6 constraints, right? Don't attack x1, x2, x2, x3, x3, x4, and so on. So we know that something has changed for x1. We want to look at other variables, right? Other queens. In order to look at other queens, let's say we are trying to look at other queens, which means that we have to look at some of these constraints, right? So which of the constraints we should be looking at? x1, x2, what might be the logic behind it? So we can perhaps try to maintain a queue of variables that say that what are the variables about which we know some information. And then from this queue, when we take out the variable, we should be looking at all the constraints where this variable appears, right? Because that's the way we can learn something more about other variables. This is why it makes sense to look at this constraint over this one. Right? Because we are trying to look at the information based on something that changed for x1. Okay, so let's look at this constraint. What can we infer now about, let's say, x1 from this constraint? Or maybe about x2? What? It cannot be placed on 1 or 2. So let's just focus on the first thing. It cannot be placed on 1. Why so? If we were to have x2 to take value 1, then what happens to this constraint? There is something about. So what happens to this constraint now? If x2 were to take value 1? Yeah.
Fails.
It fails because there is no value in for x1 that we could assign out of the current domain so that the constraint would be true. So what we are trying to conclude is that there does not exist a value v that belongs to the current domain of x1 so that the no constraint of, no attack of v comma 1 is true. If x2 were to take value 1, then for this constraint there is no value to x1 so that the no attack of v1 is true, right? Because there is no such value, this implies that x2 cannot take value 1. Similarly, if x2 were to take value 2, then there is no value for x1. Why are we concerned about x1? Because in this constraint, x1 is the other variable that appears. What if we had many more variables? It was x1, x2, x3 in a constraint. What would we do?
You'd still look at x1 for the other variables, x2, x3, x4 to see that.
We would look at that, is there some value to the rest of the variables in their current domain that we can assign so that the constraint holds true, right? Every time we reach the following conclusion that if a variable were to take a certain value, then there is no value to the rest of the variables in their current domain so that the constraint would hold true. Okay? Whenever we reach such a conclusion, we can then infer that x2 cannot take that value, right? So in general, what would it look like? That x2 cannot, if x2 were to take value u, and for rest of the variables, if there is no value that we could assign to the rest of the variables, okay? Or the set of values we could assign to the rest of the variables so that a given constraint is true, in that case, we can conclude that x2 cannot take value u. So every time we are inferring, our inference always looks like, look, here is the value a variable cannot take. For example, this one says x2 cannot take value 1. Now we learned that x2 cannot take value 2 or u here. So what we have learned is that x2 cannot take value 1, x2 cannot take value 2. What should we do now? Yeah.
I would look at x3 and do the same thing we could bring up for x1, x2 this time.
Which constraint should we look at?
No attack, x1,
So what we are doing right now is that, remember we learned something about x1. So it makes sense to go over all the constraints where x1 appears. And from each of these constraints, try to infer something like this. And every time we infer something like this, what else should we do? Because we'll infer something about x2. So it would make sense in future to do something about where x2 appears, right? So in our queue of the variable that we are dealing with, right now we are dealing with x1, so that is already empty. We should add x2, right? In future, we should also look at all the constraints where x2 appears.
And then we would put the x2 there right after we looked at no attack x1, x2, x1, x1, x2.
We put x2 there because we were able to deduce some new information about x2.
So we would then just pop off x1 off. Will we pop x1 off of our queue after we do x1, x4?
We pop x1, we put x1 in our queue when we learned something, when the current domain of x1 changed, right? We put in the queue, then we popped. x1 we have already popped. We are going through all the constraints where x1 appears.
Oh, so it's already popped when we're looking at it.
It is already popped, right? And now we are just looking at all the constraints where x1 appears. I'm just writing down these constraints. And now let's look at the constraint where we already looked at one such constraint. What are we going to be able to infer from the constraint that says not take x1, x3? We'll go over every variable, right? Here. And we would be able to figure out that for x3, x3 cannot take, what are the values it cannot take? 1 and 2 or 1 and 3, right? This also means that the current domain of x3 has changed, right? If the current domain of x3 has changed, then in our queue we should update x3, right? What about not take of x1, x4? We will be able to infer that it cannot be 1 and 4. So we should go and okay. We have now gone over all the constraints where x1 appeared, right? So now we are done with x1. Now we have to pick the next variable from the queue. Let's just say that we are going to pick the variables in the order we added, right? It's a queue. So we should now look at all the constraints where x2 appears. So let's go over such constraints. So maybe the first constraint where x2 appears is no attack of x1, x2. What can we infer from the constraint no attack of x1, x2? Look, for what values we should be making this test? Or the values that are in the current domain, right? Maybe it's a good idea for us to figure out, after we have done all this, what is the current domain of x2? 3 and 4. And what's the current domain of x3? 2, 4. This is. Okay, so what can we, from the constraint not have attack of x1, x2, what can we infer?
When do we add it to our queue again, or do we leave it outside of our queue?
When do we add something to the queue? When its domain changes, right? We don't add something in the queue just because we are looking at it. We add something in the queue because its domain has changed. Its current domain has changed. What do we infer from the constraint not take of x1, x2? So the check that we are supposed to do is the following, right? If x2 were to be assigned a certain value, then does there exist a value to the rest of the variables so that the constraint can be true? Here, of course, we are doing that there does not exist any such value. Let's see. So for x2 equals to 3, does there exist a value to x1 so that the constraint can be true?
Does the value have to exist inside of x1 domain?
It should exist inside x1's current domain.
So it can pitch.
Yeah. So does there exist a value? It does, right? What is that value? 1. What about when x2 is 4? Does there exist a value in x1's domain? There does, right? We can do this check for all the variables that are in the constraint. Let's also do the check for x1. When x1 is 1, does there exist a value in x2's domain so that the constraint is true? What's that value? Three, right? 3 or 4. So what can we infer something? Nothing. Okay, sometimes you just don't get any more information. All right, so that was one constraint. It did not help us much. Okay, let's try to look at another constraint. What about not take of x2, x3? I'm also going to pictorially draw here to talk about things that we have inferred. What about not take of x2, x3? Remember, we are just going over all the constraints where x2 appears, right? Let me also write another constraint that we had to visit at some point. Yes. So if x2 were to take value 3, does there exist a value in x3's domain so that the constraint would be true? There does not exist, right? There is no value. So what do we learn? That x2 cannot be 3. What about x2 taking value 4? Does there exist a value in x3's domain so that the not take x2, x3 would be true? It would be, right? But now we learned something about x2. What should we do now? We should add it to the queue, right? We had popped it, but now it goes back to the queue because we learned something about x2. What else can we learn? What about if x3 were to take value 4? Does there exist a value in x2's domain so that not take would be true? So if x3 was 4, then also there doesn't exist a value in x2's domain so that the constraint would be true. And that implies that x3 cannot be 4. Okay. Let's look at this constraint, not take of x2, x4. What can we infer? We have to go over all the variables, right? Let's go over first x2. If x2 were to take value 4, is there a value in x4 domain so that not take of x2, x4 would be true? Is there such a value? 3, right? So let's maybe go over x4. If x4 were to take value 2, is there a value in x2's domain so that not take of x2, x4 would be true? No, right? So what we are going to be able to infer now is that x4 cannot take value 2. We should also add x4 in the queue. It's already there. Okay? All right, we have gone through all the constraints where x2 appeared. But as we went, we also added it back to the queue, right? If we added it back to the queue, then we can again pop it out of the queue. Or maybe we could pop the variable we added, like we added x2 back to the queue, maybe in the following order. So maybe we can now pop the variable x3. What we are going to do now, we will go over all the constraints where x3 appears. Okay? What are all such constraints where x3 appears? No take of x1, x3. Maybe you can quickly help me to figure out what can we infer from no take of x1, x3. Nothing. What about from no take of x2, x3? Huh? There is no new information because when x2 takes value 4, there is a possibility that you can place x3 at 2. What about from no take of x3, x4? Because if you try to assign x4 to 2, then there is no value in x3's domain, in the current domain, so that the constraint is true. Same for x4 taking value 3, right? So the first thing we'll learn is that, look, x4 cannot be 2 or 3. But now something looks strange because the current domain of x4, what happens to the current domain of x4? It becomes empty. And empty is not good news because every variable has to take some value. So the check is at any point if something becomes empty, we should backtrack. So you see, we haven't assigned any value and now we are able to backtrack. Okay. We had learned all of this information though, so let's try to see. What do we do about everything that we learned so far when we are backtracking? Should we keep it? Huh? All the inference we made was based on the current assignment. So one idea would be to just forget all of it and restart, right? But there are more sophisticated techniques out there that try to figure out which of the information can still be written. Okay, but for now, we are going to say we have to restart. Okay, now we have now restarted. The only thing we know is that the domain of x1 is 2. Everything else can take all possible values for now. Okay. What should inference do now? Because x2's domain is 2, so we have to add x2 to the, sorry, x1's domain got changed. So we add x1 to the queue. And now we go over all the constraint where x1 appears. Let's try to quickly make progress here. What are we going to be able to learn about x2? It can't be 1, 2, or 3. What about x3? What about x4? Can't be 3. What else can we learn? Because we learned something about x2, we should look at all the constraints where x2 appears. What we will be able to learn is that all the constraints where x2 appears, from x to x3 we don't learn anything interesting. From x to x4 what do we learn? x4 cannot be 4, right? Because then there is no value for x2. Sorry, from x to x3? Ah, yes, you're right. So we learned that x3 cannot be 3. Okay. Now we go over constraint like x3, x4. What can we learn from x3, x4? x3 can't be 1 or x4 can't be 1? Huh? x4 can't be 1. We have to also go over constraint where x4 appears and so on. And you will realize we won't be learning anything more, right? There is something nice that has happened now. The current domain of all the variables, just one value. We are going to be able to just place the queen over those values. Okay, so let's try to sum up the algorithm. What is the entire algorithm? So whenever for some variable the current domain changes, okay? So we take an action that changes the domain of, if certain action leads to change in domain of a, change in current domain of x, if we change the domain, then we add x to the queue. From the queue, we pick out a variable. We go over all the constraints where this variable appears. And for each of the constraints, we do the check like that, which says that, look, if you have a constraint, let's say some constraint that is over variables x, y, z, then we say that we are going to go over one of the variables. So we are going to say that if I were to assign x to u, is there a value to rest of the variables? Okay? Are there values to the rest of the variables? So in this case, there are two variables, y and z. So we are interested in asking, does there exist value v and w? Okay? So that c of u, v, w would be true. If such a thing is not possible, then we are going to be able to infer that x cannot take value u. For every constraint where x appears, you go over all such constraints, do this check for all the variables in the constraints. So we had to do the similar check for y and similar check for z. Once you fix one value to the variable, is there a value? Are there values that we can assign to the rest of the variables so that the constraint is true? And if this is not possible, then we can deduce that, or what we call, we can infer that x cannot take that particular value u. And every time we learn something like this, then that current domain has changed. So we add that variable to the queue. We keep doing it until what can happen? Either the domain of the one of the variables is empty, or what else? We find a solution. Are we guaranteed to find a solution? Maybe we can try to figure out what can happen in case of 5 queen. Okay, let's say we place the first queen over here. What are we going to infer now? Can you quickly try to work it out? At least convince your neighbor.
X2 can't be 2. And X3 can't be 1. Assume that. So here now we assume that x2 is 3, and then we keep going until we find a solution or 1 plus x. Is that basically
Can we infer anything else
from x1?
for rest of the variables? For example, we know that x2 cannot be 1 or 2, x3 cannot be 1 and 3, x4 cannot be 1 and 4. What else? Can we infer something else?
So we look at x2. So the x4 can't be 3, right?
x4 cannot be 3. X4 cannot be 3. Why so?
Because then 2, 3, and 4 will
There won't be any value for x5, right? What else can we infer? x3 cannot be 4. Why so? If x3 were to be, then there won't be any, right? If x3 were to take value 4, then there is no value x2 can take. So that, what else can we infer?
can't do. Oh,
x5 cannot be 2. Why so?
This and this the x4 5. Sorry. And this
What about x2? Can x2 be 5? Will we be able to infer that? All right, there are two questions. One, can x2 take value 5? No, that just requires you to figure out placing queens, right? If x2 were to be 5, you can figure out that you won't be able to place 3 and 4 queen, right? But can we infer that x2 cannot be 5? So that's crucial, okay? The inference check is always with respect to a single constraint. So it is inherently limiting. But look, that's okay, because remember, in the worst case, the algorithm will take exponential time. So what we are trying to do is come up with some algorithm that would do something in polynomial time, something that's fast enough, right? And then we can always backtrack. So something in polynomial time, we won't be able to figure out that, well, not the way we are implementing inference right now. We won't be able to figure out that x2 cannot take value 5. So when inference stops, it does not mean that you could assign every variable some value and there is a solution. Okay? All we know is that from the inference that these are the values you can't take. It does not mean that the values that are still possible, you can definitely take them, right? And get a solution. That's number one thing. Inference is not guaranteed to find a solution or backtrack. Okay? All right. So now let's try to okay, I'll now go back to algorithm. We will look at the algorithm on the slide, but this might be a good point for you to ask any questions about inference. So we go over what we do, we go over the variables, we pick out the constraint, the variable appears in our, for every constraint, we do this check for every variable. Every time we can deduce that if the variable were to take a value, then there is no value to the rest of the variables, so that the constraint would be true. If that happens, then we know that the variable cannot take this value. Okay? And we keep going on. I already said that it's polynomial time, but how do we know it's going to terminate? Is it possible that we just keep going forever? Why? No, but in this case, neither of the two things happened, right? We did not backtrack, and nor we found the solution. Huh? We stop when Q is empty. But can we add the same variable to the Q multiple times? We did add, right? Yeah. Well, you have finite number of x, but you can keep adding them a lot of times, right? Because when we add an x to the q only after we derive something like that x cannot take a value, right? And the domain of every variable is finite. So there are only so many times you can say that here is another value you can't take, right? And that's why the algorithm will indeterminate. What we have looked at the algorithm right now, you can see that there are many opportunities to improve it, right? You can figure out what variables to pick from the queue, maybe figure out don't add a variable if you know you are not going to deduce something useful. So there are, of course, much more improved versions of the algorithm that have been discovered over the years. Okay. So we talked about this already. These are the slides. But I just want to go over the algorithm for a minute. So what we do, we initially made some assignments. So we add that variable to the queue. Now we keep going until the queue becomes empty. We pick a variable from the queue. Now for every variable that for every constraint this variable appears on, for each constraint and every variable that appears in each constraint, we do this check. Okay? And every time we discover that, look, the domain of the variable has changed, then we add that variable to the queue. Every time there's a change in the domain, we add the variable to the queue. And if the domain of a variable becomes empty, you immediately return failure. And that would mean the algorithm would backtrack. Last time we did discuss few things. One was, it looked like we are doing a lot of work. And what can go wrong when you are doing a lot of work? Keep taking a lot of time, right? Time is of essence here. So maybe one thing we could try to do is that, are there optimizations here that we could try to pursue that so that sometimes we would save on time? Remember, AI is all about trade-offs. You can save on time at the risk of inferring fewer things, right? So of course you could save on time by not even running this algorithm. We already saw that that's not always a good idea, right? So now we have to find other balances. So looking at this algorithm, can you think about the opportunities of improvement? How can we save on time? We have this queue where we keep adding these variables, right? So if we want to save some effort, then we should add fewer variables, right? Which means that we should make our test that we are doing when to add the variable stronger. I'm just going to tell you two heuristics. There are just two possible heuristics in the space of all possible heuristics, okay, that turned out to be useful. I don't want to tell you that these are the only two ways of saving time. So let's try to think about two simple heuristics. So we add the variable every time there's a change in the domain. We add it in the queue. What can we do? That we are already doing, right? If there is a change in the domain. You could say that, look, the change has to be bigger, right? So one is to focus on the change being bigger. Another very simple algorithm is don't add to the queue, right? You just go over one variable and don't add things to the queue. And another heuristic that turns out to be very, very effective. Add something to the queue. Add X to the queue only if the current domain of X becomes 1. This looks like very restrictive, but turns out to be really powerful, in particular for the problems where the domain might be just 2 values. Okay? And that's, of course, the problem of Boolean satisfiability. But sometimes you can say that, look, I'm going to add it in the queue only if you have really reduced the domain. Okay? But you could also say that the change has to be greater than certain threshold. You could also say that, look, I'm going to add a variable to the queue only a certain number of times. Okay, at some point I give up, let's do the backtracking. Okay? Okay, so now let's go back to so we had looked at this Sudoku puzzle. Just to remind you from last time, so if we run without inference, then on this puzzle, let's see how long it takes. It takes about 2.9 seconds. if you run with inference, then it takes about 200 milliseconds. Okay, so you can see that it's significant 10-factor improvement. It's also interesting to see what it is doing. So let's try to look at the trace of the algorithm. So what does it do? You see, it assigned the value 1. Now, in the visualization, we are going over all the squares where we are able to deduce that you can't take certain value. Okay? These, in the Sudoku, these are the squares which are it's right now representing the current domain of all the variables. So we are going over all the squares. So you can imagine that we have made only one assignment and now you keep going over all these squares, right? Every time you learn something, you add it in the constraint and then you keep going over squares. So look, inference is doing a lot of work. We have made only one assignment so far. Now we made the second assignment, okay? Now we have made assignment in the first row completely. Those two variables anyway have only one value to take. So this turns out to be a hard problem. And the reason it is hard is that so far we have made these assignments and everything seems to be going okay. But now we got a backtrack. So you can imagine we have made assignments to the entire first row and the second row. And then we figure out, oh, it's backtrack. That's a lot of effort for a normal human to do. And now you see there's a backtrack. It's a very hard puzzle because you keep making a lot of assignments. It says all good. And then you keep going back. Okay? Okay, so now let's go back to what did we discuss so far. So far we discussed this algorithm infer, and we also discussed these two ideas. One is called forward checking, where you don't add another variable to the queue. Okay, you just don't want to do a lot of work. And unit propagation, when you add something to the queue, only if the domain is 1. Two things that we were making, we were sidestepping so far is that look which variable to pick first. Okay? And the other question was that what value to assign to the variable, right? You should not, there is nothing that says that, look, if you are trying to solve n queen problem, you should start in the top right corner, right? Or top left corner. So how do we come up? Again, there is a lot of algorithm that we have derived over the years. Maybe it's how do we come up with these heuristics? So one way to visualize is most of us try to solve heuristics all the time. Suppose you want to go out with a group of friends, okay, for a dinner. Some of your friends one of your friend is very busy and you are trying to figure out when to go out for dinner. What do you do? If you know that one of your friend is very busy. So first thing is to ask your busy friend when the busy friend is free, right? Because it doesn't make sense that you come up with the entire plan and your friend who is very busy says that, look, it doesn't work out, okay? So another question whether you should have such friends. Suppose somebody asks you, when are you available for dinner? What should you try to tell them? If you actually want to go out for dinner with them. Greatest number of options, right? It's not a good idea to say that, look, I'm available for dinner only between 6:10 and 6:15. So we can apply those lessons to our CSP world also. What variable to pick? Well, the variable that is most constrained, that appears, so that has the fewer possible values. So that's a good heuristic to pick a variable. What value to pick? Well, we should pick the value so that it leaves out possibilities, right? You should try to suggest a slot that would be available to as much people as possible. Okay, so that it puts less constraints on others. There is a duality that we are trying to look at here. What we are trying to do is that we don't know if this set of constraints is satisfiable or not, if there exists a solution. So what we want to do is that, look, if there is no solution, then I should know immediately. So it makes sense to go with the BJ's friend. But if there is a solution, then give me an assignment so that I could satisfy everything else. So when we are picking the variable, we are really hoping that we immediately get to the solution. When we are picking, value, and when we are picking variable, we want to see that if there is nothing that can work out, then you immediately tell me. The power of these solvers comes from the fact that they can look at this entire space and implement these heuristics, which are often very hard for us humans to do. So look at this puzzle. What do you think should be the first square that you should try to fill in? Let's try to guess. Have you played Sudoku? All right, so let's try to see. What would you try to do? Row 6? What else? Row 6, column 4. That's very particular. What else? It's okay to just guess an area.
Column 8 looks pretty good too.
Column 8. Okay. What else? Let's see how close you get to the algorithm. I gave up on playing with Sudoku long ago, once I learned how the CSP solvers work. All right, so let's see. Where do you think it's going to pick the first value? Column 8, row 4. Okay, I think what have you got? Let's see. Over here, there were few ties, it had to break. What do you think is going to happen to the next? What value should we pick next? Sorry, what cell should we pick next? So first, I just went through the entire inference, and the next cell, it turns out it picks is at the top right corner. And then it picks somewhere in the middle. Then it tries to start filling this block here. Then it starts going after this one side. And it makes few choices, and you can see what I'm doing is that every time I click next step, it does all the inference. Okay, we just go to the next decision. Are you noticing something? Have you seen something hasn't happened so far? You see, we got there. No backtracking. So these heuristics can be really amazing, that you can go without doing any backtracking. It's not to say that this would work all the time, okay? But let me tell you some statistics that are interesting here. So suppose we were to run the algorithm, the improved algorithm. Let's see. This one was the initial algorithm that we started with. Oh, no.
load setting?
So remember that. So let me tell you, read out some statistics for you. So what that algorithm did is that it tried about 6 million assignments. And of course, and it ended up backtracking 720,000 times. 700,000 times it had to backtrack without inference. Once we do inference, we are down to trying 800 assignments and backtracking only 831 times. And once we do the heuristic to figure out, we don't backtrack at all in this puzzle. It's 27 assignments. So these heuristics are indeed very powerful. And now we are down to, remember with inference, we were taking 200 milliseconds and now we just take 15 milliseconds. So a puzzle that if you had started working on your spring break, you might have been stuck until now, can just be solved now with 15 milliseconds. So these heuristics are indeed very powerful. Okay, so that also gets us close to the all the things that I wanted to discuss about constraint satisfaction problem, except one last thing. Look, just like most things in life, sometimes things don't work out. And what makes sense to do? Just restart. Same thing happens to our world of solvers. Sometimes you have just gotten in one end of the search, you made some choices so far, things are not looking well. So it makes sense to give up, restart from the top. Of course, you don't want to. One issue with restart is that you should also remember where you were, right? So that you don't make such a mistake. So there's a lot of work that goes on in trying to remember where you were. You could try to write a constraint to say that, look, I was here, I should not come here again. Okay? So that, and restarts are a very crucial aspect of the solvers. In fact, the solver that you are working on in your homework does very aggressive restart. The modern solvers, what they do initially is that initially they will say that, look, I just want to quickly figure out there is a solution or not. So they will very aggressively restart. Try few assignment, didn't work out, restart. Try few assignment, didn't work out, restart. Okay? Why so? Because in practice, it turns out that for most of the problems, we have seen often it is the case that some choices just immediately lead to solutions. Otherwise, you might take a long time. So modern solvers will aggressively restart. And only after a while, it does make sense at some point. Maybe the problem is indeed hard, okay? And restart is not your solution. You will have to spend time. So then the solvers take a while, spend some time in the hope of finding solution. And if it again crosses a certain threshold, you go back to this. You restart often. You try to memorize the places you were in and it did not lead to the solution. So there's a lot of work that goes in what is called learning. These are, how do you learn information about the space that you explored? How do you represent it efficiently? One aspect that we did not talk about in this course is it's all about data structures, because you are often dealing with problems that involve millions of variables, and the solvers for a problem that involves millions of variables, a lot of these problems, these solvers can solve within seconds. Just imagine within seconds, even trying out all assignments over these millions of variables. So the space can be very large, but there's a lot of effort that has gone on in building efficient data structures. Data structures that allow you to pick the next variable, that allow you to pick the next value quickly according to the heuristic, allow you to do the inference very quickly. So there's a lot of magic that goes in building these data structures. There was a bonus slide that I will put in, which is how to go beyond backtracking. That's not something we are going to ask you in assignment. Okay, so let's conclude, we started with backtracking. We realized that, look, it might sense to infer new information. We looked at the algorithm to infer new information. Inference is not going to solve all the problems. So for example, for 4 queen, it solved the problem, but for 5 queen, we had to still go and try out other assignments, okay? We also looked at the heuristics. What variable to pick, what value to pick. And then, just like most things in life, sometimes you have to give up and restart. Okay, so with that, we have completed today's lecture. This is about 2-3 minutes. If you have some questions, you can ask. Yeah. That's a very good, and there's a lot of heuristic that go in about how to determine when to restart. It's not an easy solution because maybe you were on the right path, you restarted and you had to do all this work again. Yeah.
I guess I said like the restart starts for like a limited budget. But what do you mean by like a limited budget?
The budget can be time, the number of decisions you made, how much inference you did, and it depends on the problem.